Okay, so in this video, we're going to be talking about the laws of thermodynamics. And so just kind of how we had like Newton's laws of motion when we talked about mechanics and things moving, the laws of thermodynamics govern the realm of heat and thermal energy. And so they're kind of fundamental to dealing with this unit. And so there's more than two laws, but we're only going to focus on two laws in this class. And basically, um, the first law of thermodynamics is essentially a restatement of the conservation of energy, right? And we talked about conservation of energy a lot in the last unit. It's basically that fundamental principle in physics that says that, you have this thing called energy and you cannot create or destroy energy, but you can transform it into different forms. Now, the idea is the same in this unit, but we actually have a specific equation that we use in dealing with problems with thermodynamics, and that equation, that first law of thermodynamics, we write with an equation. And we'll talk more about this on the next slide. Um, I will also say that the first law of thermodynamics can be stated in a different way. Um, Basically, it can be stated that you cannot build a machine or a system that is more than 100% efficient. And we'll talk more about efficiency here in a little bit. But basically, efficiency has to do with the ratio of your output power to your input power. And so when I say you can't make a machine that's more than 100% efficient, basically what I'm saying is you cannot create something that creates more energy out than it takes in. Okay, because you can't create energy that would violate conservation of energy, right? Energy cannot be created or destroyed, but it can be transformed into different forms. And so if you had something that was more than 100% efficient, that basically means you're getting more power out than you put in, which is not possible because that violates the first law of thermodynamics. Okay, the second law actually has three different ways to be stated. And again, we'll talk more about this as we go through the video. But basically, here are the three different ways to state the second law of thermodynamics. Okay, so you could say, to begin with, for the second law of thermodynamics, the first statement is that the entropy of a system always tends to increase. Okay, the entropy of a system always tends to increase. Now, when you read that, your first thought should be, what the heck is entropy, and what does that mean, tends to increase? And so we'll talk about that a little bit later. Okay, the second statement of the second law of thermodynamics, and when I say there's different statements, what I mean is these three things fundamentally all mean the same thing. It's just different like perspectives of looking at the same idea. Okay, and so we'll see problems with the second law of thermodynamics dealing with different like statements or different viewpoints of the second law of thermodynamics, but fundamentally it's all the same thing. Okay, so the first one, entropy of a system always tends to increase. The second one is that heat tends to flow from hot to cold on its own. In other words, heat naturally flows from hot to cold. So, for example, if you had, let's say, you take a hot cup of coffee and you put an ice cube, we've talked about heat before. Heat is the flow or the transfer of thermal energy. And so, what the second statement means basically is if you put a cold ice cube into a hot cup of coffee, energy is going to flow out of the coffee and into the ice cube. And so it's not that the ice cube is like putting out cold energy to the coffee. It's actually the other way around. The coffee has more thermal energy than the ice cube, and heat, that thermal energy transfers from the hotter object into the colder object. Okay, and so the second law of thermodynamics, one statement is that happens naturally. Okay, heat naturally flows from hot to cold, which, by the way, might sound kind of obvious, and just for the record, it is possible to make heat go from cold to hot. In fact, that's how refrigerators work, or like air conditioning or stuff like that. You can make heat flow in the opposite direction, but in order to do that, you actually have to add energy. You have to put in extra energy. Okay, so on its own, heat naturally flows from hot to cold. And the second statement, the third statement of the second law of thermodynamics is that you cannot create a 100% efficient machine. Now, you might look at that and be like, wait, didn't he already talk about like 100% efficiency? Okay, so just to clarify, I'm saying two different things. Okay, the first law of thermodynamics says you cannot create a machine that is more than 100% efficient. Okay, The second law says you actually can't even get to 100% efficient. Okay, and some physics textbooks say this like you can't win the game and you can't even break even. Like you can't get more out than you put in. And the second law basically says you can't even get out what you put in to begin with. Okay, so one says that you can't have more than 100% efficiency. The other says you really can't even get 100% efficiency to begin with. Okay, and so we're going to go through these two laws and do problems with the first and second law in this video. And honestly, all of these calculations are relatively simple, so hopefully it's not too difficult. Before we do that, I'm going to show you a clip, and you will have, it's a short clip, it's maybe like 30 seconds, a minute long, and it's a clip from The Simpsons, and you will have a question related to that on your practice assignment. Um, so I will go ahead and link that clip in so you can watch it. And then once you've watched that clip on YouTube, you can read the explanation here. Basically, what she creates is what's called a perpetual motion machine, which is not physically possible because that type of machine would violate these laws of thermodynamics. And in the clip, he talks about it moving faster and faster, which would actually violate the first law of thermodynamics because if it's moving faster and faster, that means it's creating more and more and more energy, and you can't create energy. That would violate conservation of energy, right? And so it's just kind of a thermodynamics joke, right? But let's start off by talking more about the first law of thermodynamics in the context of this unit. Okay, so let's just introduce some terms. For this law, we actually have an equation for the first law of thermodynamics. Okay, and here is the equation. It is written in red. I'm going to tell you what everything is, and so I would recommend that you write that down and make sure you understand what each term in this equation means. Okay, take good notes. Okay, in this equation we have Q equals W plus delta U. Okay, so first of all, Q is the symbol for heat. Don't ask me why we use Q for heat. I don't know. We will see that later on this unit. We'll have another equation that has Q in it. Okay, Q is a symbol for heat. Remember, heat is the transfer of thermal energy to or from an object. Okay, and so that is measured in joules because that's the transfer of thermal energy. Heat equals W is work, and we've seen work before. Work is done when a force is acting on an object and the object moves, and so work is also measured in joules. We saw that in the last unit. Okay, right? Force times distance. When there's a force acting and some object moves because of that force. This thing delta U, so let me just go back. This thing delta U right here is what we call internal energy, which is a very fancy way of saying the energy like absorbed or stored within an object. Internal energy. Okay, so a lot of the times when you're doing problems, it might not say internal energy, but it might talk about the energy absorbed by something. Okay, so that's talking about delta U, and that's also measured in joules. Now, basically the first law of thermodynamics, if you want to think like, what does that mean? Like it's an equation, but what does that mean? Basically, on the left side, you have heat. So let's say you have like a container, and you add heat to the container. What this equation says is when you add heat to something, that energy that you're putting in can do one of two things. Either work can be done, that's the W, or the energy can be absorbed by the container itself, and it can get hotter. Okay, so on the left you have the energy going in, and basically on the right side you can think of it like these are the two places the energy can go. Okay, so if you want like a simple example, like imagine you take like a balloon filled with air. Okay, so what happens if you heat up a balloon filled with air? Well, one of two things can happen. Actually, both can happen at the same time. But let's say you add heat to a balloon. Either the balloon can expand, that means the balloon can get bigger, right? That means work is done because the object is moving, or the air inside the balloon can get hotter. Okay, and realistically speaking, both of those things would happen. Right, and so when we say Q equals W plus delta U, that's basically what we're talking about. When you add heat to something, it can go to one of these two places. It's not like an either or proposition. It can go to both of them as long as the total amount of work done plus the total amount of energy absorbed is equal to how much heat you put in. All right, so let's do some simple concept examples. Pause there if you need to look at that some more. Okay, so this is just like a really simple concept example. Let's say, hypothetically speaking, you had a rigid, unbreakable, sealed can of air, and you heat the can up from underneath. Okay, so what's going to happen if you have a can that cannot expand because it's like unbreakable? Okay, so it's made of some type of magic metal that can't like expand or contract. So what's going to happen? Well, from the first law of thermodynamics, you have Q equals W plus delta U. But if the container cannot expand because it's like unbreakable metal, then that means there can't be any work done because nothing is moving. Okay, so what that would mean is all of the heat put in from the Bunsen burner, the only place it has to go is delta U, to that internal energy. So in other words, all the energy is going to get absorbed by the air inside the can. Okay, then the air is going to get hotter and the temperature is going to go up and stuff. Now, what if you had a metal can and the top of the can can move? Like let's say you have like a coffee can or something. You put the lid on and it's got a lid, but the lid can pop off pretty easily. So what happens if you heat the can now? Well, now because the top of the can can move, yeah, some of that energy might still go to delta U, but if the top of the can can move, okay, or if it's not unbreakable metal, then that means work can be done. And so that means the can actually like expand and get bigger at the same time the air inside the can is absorbing that energy. Okay, and this you could see like don't do this because this would be dumb to do, but for example, like um, let's say you took like a soda can and you put it on the stove. Don't do this. This is dumb. Hey, I'm just warning you, please don't do this. It's not safe. But if you put a soda can on the stove and you heat it up, eventually what would happen is the can would probably like get bigger and it would probably pop and explode. Right? Because as you're adding heat, yes, some of that heat can be absorbed as delta U, but eventually the can is going to do work. Some of the energy is going to go to work, and that work is going to make the can like get bigger and like blow up. Again, please don't do that. You've been warned. Okay, so that's just like kind of like a concept example right there. This is the like answer if you want to look at what I actually wrote as the answer. Um, but that's basically what I just said. Okay, so let's do some quick calculations. Okay, so example 1.5. A cylinder holds an ideal gas at room temperature. 1,000 joules of heat is added to the gas. Remember, heat, we're going to label that as Q. How much heat is absorbed by the gas? Remember, what we're talking about there is energy being absorbed. That's how we usually describe delta U. That's that internal energy when it does no work on the surroundings. So no work means the work done is zero. All of these calculation problems are really, really basic. Okay, it's as simple as this. We write down the equation Q equals W plus delta U. Q is 1,000. For this problem, W is zero because it says there's no work done. And we're asked what is delta U? Well, obviously delta U has to be 1,000 joules. Okay, and so all the calculation problems you're going to have with the first law are really just this simple, just really basic math. Okay, even if you look at the problem on the right, it's the exact same setup, except now instead of where it says no work is done, it says 300 joules of work is done. Exact same givens and exact same setup. Okay, so all we have to do here is plug in the new value for work. We add in 1,000 joules. Of that 1,000 joules, 300 joules goes to work. What happens to the other 700 joules? Well, it gets absorbed by the gas, and so the gas gets hotter. Okay, so we have delta U equals 700 joules. That's it. Problems involving the first law of thermodynamics, very, very easy. Okay, so pause it there if you need to look at that some more. Okay, what about the second law? Well, the second law is the one that has like three different ways of stating the second law. And I have all three ways right here. Okay, so heat always naturally flows from hot to cold. That's kind of like an obvious thing. Most people don't have any issues with that. The second statement is the entropy of a system always tends to increase. So let's talk about what the heck is entropy and what does that mean tends to increase. Tends to means will happen on its own. So like heat tends to flow from hot to cold is the same thing as heat naturally flows from hot to cold. Like if you leave it on its own, it's going to happen. So you could basically think of this as the entropy of a system always naturally on its own increases. Of course, that doesn't help you if you don't know what entropy is. So what is entropy? So in a very, very, very basic sense, entropy is the measure of disorder of a system. Okay, how disordered the pieces of a system are. Like, are they nicely neat and organized, or are they kind of messy, kind of out there, kind of all over the place? Okay, it's kind of more technical than that, but at this basic level, that's what entropy is. It's a measure of disorder of a system. All right, so let me give you an example, and then you can do example 2.5 on your own. What if following are situations of a system's entropy increase? Okay, so entropy, I think, is a measure of disorder. So for example, if I take a deck of cards, like a new deck of cards, and I shuffle it, am I increasing the amount of disorder or am I decreasing the amount of disorder? Okay, so when you think disorder, think all over the place, think messy, think unorganized. Well, if I shuffle a deck of cards, yeah, I'm increasing the entropy. Okay, so yes, that would be an example of increasing a system's entropy. Now, what if I take a deck of cards and I actually sort it and I put every single card in order, like, 1, 2, 3, 4, 5. That would be decreasing the entropy of a system. Okay, what if you clean your room? Okay, well, if you're cleaning your room, are you making it more disordered or less disordered? Well, you're making it less disordered. Okay, so cleaning your room would actually decrease the entropy of that system. What if you drop a glass on the ground and you break it? Okay, well, the pieces of the glass are going to like break apart and they're going to fly apart. Okay, you're making it more disordered. Now, I want to stop here and talk about what the second law says. It says the entropy of a system will naturally increase. Okay, what I mean by that is if you drop a glass on the ground, it's going to break. Okay, that's going to happen on its own. Is it going to fly back up into your hand and put itself together on its own? No. Okay, think about cleaning your room. Like, is your room going to get clean on its own? No. Is it going to get messy on its own? Like if you just don't clean for like 2 months and you just like live your life, is it going to get messy on its own? Yeah. Okay, so those are all examples of entropy naturally increasing on its own. You don't have to do anything to make it happen, it's just going to happen on its own. Okay, so your room becoming messy over time, that's an example of increasing entropy. Okay, cleaning your room is the opposite of that, so that's decreasing entropy. What if you heat a container of gas? Okay, so if you think like a container of gas, heating it up, those gas particles are going to start moving around faster and faster and faster. Are they becoming more organized, more ordered, or less organized, less ordered? Well, if they're moving around faster, then they're going to become less ordered, which means you are increasing the entropy, and that would be an example of increasing entropy. And freezing an ice cube would be the opposite of that. Okay, so that is not increasing entropy because if you think like an ice cube, if you think like a cup of water, what happens if you freeze a cup of water? Those water molecules like they slow down, they don't move as fast. They like become compacted together, right? As it goes from like a liquid to a solid, they stick together. Those water molecules. Okay, so that would be decreasing entropy because they're becoming like more ordered, less chaotic. All right, pause there if you need to look at that some more. Example 2.5, I want you to try to do example 2.5 on your own. Really quickly, which of the following is not a situation which would lead to an increase in entropy? Okay, so pause there and try to answer that on your own. Okay, all of these are situations that would lead to an increase in entropy because everything is becoming more disordered except for answer choice B. Because if you're sorting M&Ms um, by color, you're creating a system that is more ordered, more organized than it was before. So the correct answer to that question should have been B. All right. Okay, so that is the second statement of the second law of thermodynamics. And just really quickly, we're going to talk about efficiency and then we'll be done. Okay, so let's talk more about what efficiency is. Remember, according to the first law, you can't have more than 100% efficiency. According to the second law, you can't even get to 100% efficiency. So what is efficiency? Okay, well, we can calculate efficiency um, by basically doing output over input. So usually you're talking about like power, right? Output power, how much you're getting out for divided by how much you're putting in. So the symbol for efficiency, we write like a lowercase e, and it's just going to be output over input. And because usually it's as a percent, if you want, you can think like times 100, that just makes it a percent. Okay, so for example, like if you had an efficiency, let's say you do a calculation and you get like 0.7, that would be 70% if you multiply by 100. Okay, so sometimes you're given efficiency as a percent. In order to do a calculation, you would probably have to divide by 100 to move it from a decimal, to move it from a percent to a decimal. Okay, so just kind of keep that in mind. Efficiency is just output over input. Okay, so just really two quick examples. Example 3, you've got a light bulb, and it says the light bulb consumes 200 joules of electrical energy per second. That's not a trick, by the way, but joules per second is watts, and so it's saying that the light bulb uses 200 watts. Okay, so 200 joules per second, 200 watts, same thing, but only emits 25 joules of light energy per second. Okay, so that's 25 watts. What is the efficiency of the light bulb? Now, people always get tripped up by like, how do I know which one is the output? How do I know which is the input? Well, it depends on the context. Okay, so imagine the light bulb. You have energy going into the light bulb, and then you have energy coming out from the light bulb. Okay, what is the energy coming out from the light bulb? Well, that's light, right? So that 25 watts is going to be the output. Okay, what about the input? Well, the input has to be the other one. Okay, so it's going to be 25 divided by 200. Okay, and if you calculate that, you get 0.12. And if you want to write that as a percent, you multiply by 100 and you get 12.5%. Okay, so that's the efficiency of this light bulb. Not very efficient, right? Okay, and by the way, you might ask like what happens to the rest of the power because you can't just like destroy energy. Well, it gets wasted as heat, and so that's why some light bulbs get hot when you leave them on after a while because the other like 87.5% of the energy goes into heat, and so it gets hot. Okay, so like if you have a light bulb that's like really low efficiency, they would produce a lot of heat. Like if you've ever played with like an easy bake oven, the light bulb in the easy bake oven is probably really low efficiency. I also want to say that if you're worried about like how do I know which one is output, which one is input, there's another easy way to check, right? Because you can't have more than 100% efficiency. That would violate the first law of thermodynamics. All right, so let's say you do this calculation. If you like flipped it around and you did it the other way, that you would do 200 divided by 25 is 8, which is 800%. Well, you can't have 800% because that would violate the first law of thermodynamics. And so it only works one way. And so, some people like the only way you could possibly mess this problem up is if you get the numbers flipped. But if you get them flipped, then you should recognize like, hey, this can't be right because this number is more than 100%, right? So efficiency, output over input, don't forget to convert to a percent by multiplying by 100. But that's basically it when it comes to the laws of thermodynamics. All right, so pause there if you need to look at that some more. Okay, and just to do a really quick example, look at example 4. I want you to use the picture on the right to calculate the efficiency of this light bulb as a percent. Okay, so look at the values right here. What is the efficiency of this light bulb? Okay, well, if you look at how much is going in, that's the input. The output comes out in the form of light. And so if efficiency is output over input, then 9 divided by 100 is 0.09. And as a percent, that's 9%. Ta-da! All right, so that is it for the laws of thermodynamics. As always, please let me know if you have any questions, and I'll see you guys in the next video.